Hello, welcome to FoLT Lecture 10, our second lecture on classification for natural language processing. My name is Ivan Habernal from the Trustworthy Human Language Technology group. If you like what you see, I'll be happy if you click on like or put a comment, or if you have any question, just we can discuss it here in the comments on YouTube because it's a public lecture basically now. Today, we're going to talk second lecture about automatic classification, something we opened already in the last lecture, and we'll be dealing with some advanced topics as well as with some evaluation, and this is where we start with. When we want to evaluate our learning algorithm for natural language processing, well, we are interested in more, let's say, quantitative analysis than just here excellent, good, and satisfactory. So what we are going to do is to assess the performance of the model, and we want to get the prediction error on some reference data set. This is something we already were talking last time about, but here we are somehow specify the data set, the reference data set. Typically, we call it a gold standard data set because it's a data set which is typically hand-coded or annotated or labeled by humans, and since human time is worth gold, we call it typically like gold standard or the single source of truth. So if we have a learned classifier, we compare our predictions, or we let the classifier predict on the gold standard data and simply compare the predictions with the gold standard, and this will give us the prediction error. We have actually two reasons why we want to evaluate our learned classifier. And one goal is model selection. So let's say we have different models. For example, we have a naive-based classifier, and then we have one logistic regression, and then so on, so on. So something we were talking already last time. And we want to choose the best model. Or we want to, it's called model selection. We want to tune some features. So for example, feature engineering, again, as we talked last time, we're showing that feature engineering could be a manual effort. And we want to make sure that the features we are adding are actually helping the system to learn better and not making it worse. Or you want to tune some, so to say, hyperparameters. So the hyperparameters could be some constant, for example, a size of the vocabulary could be one hyperparameter. So we could have a model which only works with the most frequent 10,000 words from the language, or we could have a model that works with 100,000 words, most frequent words from the language. So this is some sort of hyperparameter, and we might want to tune, so to say, these hyperparameters as well and evaluate them to see which model and which hyperparameters work better. Once we are sure that our chosen model is best on some data set, I will come to this later, then we perform something which is called a model assessment. So having the final model, the best one, we want to estimate its performance on some new unseen data, and it will tell us something about the generalization capabilities of the model. So how well the model generalizes on something which has never seen before, so new data. And as you might guess now, this is something what we touched already in the last lecture. We split our corpus or our data set into three parts if we have enough data. So we take some random sampling or random splitter and have three parts in the data set. We have the training set, so this is where we train the model on. We have the dev test set or dev set, and this is something where we evaluate our model selection. Typically, we evaluate our models and tune the hyperparameters and pick the best model on this data set. And then we have this test set, which is something held completely out, and this is where we test our generalization error. One special thing about a test set is that it has to be untouched for the whole process of experimenting, and basically evaluated, so the models can be evaluated on the test set only at the very end. If we touch the test set during our feature engineering or hyperparameter tuning, and we say like, well, okay, I'm now curious how it works on the test set, we're coming into the risk that we actually starting overfitting our model to this particular test set. Very, very easy to do. So unless if you have the access to the data, it's very tempting to use the test data to actually, have a better model. And this is something which actually happens quite often in research as well, when we might have, as a community, we might have some standard test data sets, for example, for part of speech tagging, and the same test set has been used extensively over, let's say, a decade or maybe for 20 years for new algorithms and new algorithms and new algorithms, and the models are getting better. But what we are also doing here is that, reusing the same test set and having access to the same test set over and over, we are overfitting to this particular test set. And we don't know whether the model really generalizes on other domains. So for example, in case of part of speech tagging on pen-distorts tree bank, this is the case where the model were actually overfitted over time. So keep in mind, if you have a new fresh data and you have the test set, just keep it somewhere on site and never touch it before running the final experiment, maybe for a paper or before the model goes to production. Or you risk then overfitting. If you are in the position of creating the dates test set by yourself, you might want to consider, let's say, some constraints. So it could be super random. You take just the set and split it randomly completely. Or you might want to take some, maybe like a newer part. So for example, if your data set spends some period in time, what you typically want to do is to learn the model on the past, then validate on some, so for example, your data comes from 2010 to 2020. So you might want to split the data set for having 2010 up until 2018 as a training set, then 2019 as a def set, and then 2020 as your test set. So you would model then basically generalization and learning from the past for the future. This is an ideal case if you have the chance. So it could be like distinct from the training set. It should be large enough because you want to have a good estimate of the errors you're making. If you test only on a few instances, you never know how much chance there is. So, some statistic significance plays also a role, and you want to make sure that your test set is large enough to draw meaningful conclusions. And at the same time, you don't want to have your test set very different from the training set. So the domains should be somehow related. In reality, you never have enough data. In very exceptionally, you have very much enough data. Typically, you have lesser data than you need because gold annotation, human annotation is costly, and so on. So you are never really enough. You don't have enough data. So you want to still run the the train, def, and test split on the small data set and evaluate your learn accuracy or learn model performance. So you can basically split the data set in a repetitive manner. So you split your train, def, test multiple times on the very same data set, and then always train on train test, evaluate on the def set, the hyperparameters and fine tuning, and then you have the test set. This methodology is called cross-validation. So how exactly cross-validation looks in practice is that we have something called k-fold cross-validation. So the k is number of folds, and we split the whole data set into k different folds randomly at best, and then we repeat train and test on the different folds. How exactly will be clear in the next slide. So here we have a k5 fold, and these are five folds of the same size from the corpus. Here's an example of 10-fold cross-validation. So what we are running here, we have 10 different runs. So k is 10. And in the first run, we take the 9 folds for training our model and one FoLT for validation. So this is where we run our train model from here, we evaluate it here, and keep the result somewhere. And we repeat that. So then we train on FoLT 1, 3, and so on, and validate on FoLT 2. So this is not rocket science. Basically, we need to go through the loop and evaluate on each FoLT and train on the others. And then we take these errors, and the final error or the final model performance is measured as basically the average. So we take 10 E's and sum up and divide by number of FoLTs by 10. So, but remember, we still would love to keep the test set completely out of this cross-validation, because if we take the full data set and run cross-validation on that, we would be somehow fitting to the training data. So imagine you start doing your experiments. You take your data set, run cross-validation, split to 10 FoLTs, and start, and you get the results. For example, 81 accuracy. And you say like, well, maybe if I add more features here, or if I take a better model. So you start experimenting, and then you run the same cross-validation on the very same data sets, and you get maybe better results. But you don't have any external test benchmark data to really see whether you are not just overfitting to this particular set by this cross-validation. So in the ideal case would be that you take a part of development set, you run your model selection there using the cross-validation because you want more data for training, and then still you apply it to some test set. This is the ideal case. Now we will introduce a couple of evaluation metrics. We mentioned some of them already in the previous lecture with a short explanation. Most of them are sort of common sense. So when we, for example, talk about accuracy, we somehow feel, well, accuracy is how accurate my classifier is, which means how many times it answers the proper answer or classifies the proper class. In particular, and that's true, in particular, it's just a fraction of the correctly classified items. So for example, if we were saying the blue and red dots, so how many times for the blue one we said blue, and how many times for the red one we said red, divided to all instances in our test data. So this is like a percentage between 0 and 1. 100% accuracy is like that the model got everything right, and 0% accuracy, it got everything completely wrong. It's typically not the case. We have built-in capabilities in NLTK for this evaluation, where we have the method accuracy, where we put a train classifier and the test set we want to classify on. And it returns a double, which we print out here, formatted to 2 decimal points. How do we understand accuracy? So there's accuracy has some properties that reflect the true distribution of the labels in the gold standard data. So for example, let's classify word senses. So word sense disambiguation, and we have the word bank, and we say in most of the cases it's a financial institution, and the other sense, River Bank, is just in 5% of the data. And if we take the most common, so the most frequent baseline, so very dumb model that says like what is most frequent will be classified as such, we will get 95% accuracy. So if we see bank anytime and we see, well, it's financial institution, just because of this the distribution of the classes, we get 95% accuracy. So we were just guessing the majority baseline or the most frequent baseline, and we get pretty good accuracy. So you really need to understand the context or the class distribution in the gold standard data to really understand what accuracy means, what a score means, because there could be imbalances in the classes in the data. If we have balanced corpus, so for example, financial institution would be only in 4 cases, and there could be 16 other classes, then the most frequent baseline, just by guessing, would give us only 20%. So, this 95% is almost impossible to achieve when the class distribution is much different. So take it into account when understanding accuracy. If you see a model that gets 99% accuracy, it doesn't mean anything unless you know what the true distribution of the gold label classes is. If the distribution is 50-50 and you get 99% accuracy, then your model is really, really, really good. If your distribution of the classes is 90-10 and you get 90%, then, your model is basically guessing the majority baseline. So it really depends on the context. And this is an example, this sort of skewed distribution is an example in information retrieval. So when we search for a document, so we have a query and we want to find a document in a collection. And we want to classify it as relevant or irrelevant, so binary classification. And of course, if we have 100 million documents and there's only 100 documents relevant, so very small fraction, and the majority is irrelevant, if we have a classifier that says every returned document is irrelevant, we will achieve almost 100% accuracy because it's true, because of the distribution of the true data. So we need maybe some better metric that takes into account this unbalanced distribution of the data and will tell us something more meaningful about the actual performance of the classifier. We do have such a metric, and they come in different names in different domains. So in information retrieval or NLP, we have precision, recall, and F-measure. But maybe in a medical setup, we have specificity or sensitivity, and these all metrics are based on a common format called confusion matrix. And in confusion matrix, so we have one example of confusion matrix here. It's not really a matrix, but we have 4 different sets. What this true positive means that the document we were queried was relevant and the system returned it. So it was retrieved and it was classified as positive, as something which is really relevant. Then, so it's correct. Then true negative is that the document was irrelevant and our system didn't return it. So for example, we typed the query and the document wasn't really relevant to our query and our system said this is irrelevant, so this is fine. Then we have 2 other classes which also are important, it depends on the distribution of the data. So false positive means that the document was actually irrelevant, but our system was falsely predicting it's positive and retrieved the system, and it's wrong. So again, the gold label here was irrelevant, but our system said relevant. And the other false negative is actually the opposite. So the document was relevant, but our system said falsely, well, it's negative, so we didn't retrieve it. So we have 4 different classes. It might be tricky to remember a little bit, so I suggest to go to Wikipedia and read more about it. What is true positive, true negative, false negative, and false positive. These are important things to remember in any sort of testing. If we are now in the middle of corona pandemic, you hear about different tests and their specificity and sensitivity. So basically it's based on confusion matrix and true positives, true negatives, and so on. So it's actually very helpful to understand what they mean. And based on these true negatives, true positives, false negative, and false positives, we have 2 metrics. One is called precision. So it's how many items that were identified were actually relevant. So how precise the algorithm is. The other is recall. So we are retrieving some documents and we are interested in how many of these retrieved are important. So these correspond to different views on the confusion matrix. So having just two numbers is not really helpful for evaluating a single system. So compared to accuracy, for example. So we have something called a F1 score or F measure. And this is 2 times, it's a geometric mean of precision recall. So 2 times precision recall divided by precision plus recall. So it combines these two measures together and give a single score. Precision recall and F measure are all between 0 and 1, with the meaning that 0 is very bad, it can't be any worse, and 1 is a perfect system. In NLTK, we have confusion matrix capabilities built in already. So for example, these are our gold standard data. These corresponds to the classes actually. So class 1, 2, and 3. And the system predicted these, this vector or this list of predicted classes. And we run confusion matrix, create a new instance of confusion matrix, and pre-print the matrix. So now it really looks like a matrix where here the rows or the header of the row corresponds to gold standard data, so the true, and here the columns correspond to what the system predicted, what the model predicted. So for example, here this one, so and here these numbers are just counts, how many times this occurred. So we can try actually to count it in the data for gold standard class 1 and predicted class 1. So gold standard class 1 is just 1 and 2 occurrences and no more. So this is the integer here, 2 occurrences of 1 gold and 1 predicted. 1 gold and 2 predicted is actually only once here, and this is it. So you get a gist. So basically this is how you construct the confusion matrix. It's just basically counting the gold and the prediction and putting into the matrix. Also now we can, from the confusion matrix, we can also compute the accuracy. So the accuracy is the diagonal, and the diagonal, we just sum up the diagonal. So 2 plus 1 divided by all instances, and this is our accuracy. Now how we compute the precision. So precision is the fraction of the truly predicted classes divided by all predicted as such. An example, so precision for class 3 would be how many of them were predicted as, how many 3s from gold standard were predicted as 3 divided by all predicted as 3. So how precise is our classifier on class 3? So in this case, this is 1 here over all of the years, so 1 plus 1, which is 50% precision for class 3. What is a recall for the same class? So recall is how many of the retrieved, how many of the true ones were retrieved as such. So we take again here, so the correct predictions divided by the sum over the row here. So this is 1 over 3 is 33% recall for this particular class. Here's a quick visual recap. Again, accuracy and precision and recall. So remember, these are gold standard labels and these are predicted. If you get a confusion matrix, this is which is transposed. So here the predicted and here the gold standard, everything changes. So, make sure that you know what the confusion matrix is really showing, because there is no, it's not standardized. I mean, it's typically used as such, but it could be other way around. So you want to understand not only visually, but also what is precision and recall, what it actually means if you know what these labels are. But for this case, again, this is gold standard and this is predicted. So accuracy is the fraction of correctly classified items. Precision for a class, so for example, for class 3, it's a fraction predicted as class 3, so true predictions of 3, that belong to class 3. And recall is fraction that belong to class 3 predicted as class 3. So visually accuracy is computed from the diagonal, precision is computed as a column, and recall is computed as a row. So we know how to evaluate our algorithms, and we are coming now to something I would call as a machine learning model zoo. So we'll go through a couple of different models and introduce them a little bit. And most of them are, I think all of them are actually in NLTK and just, out of box, easy to use. And we'll spend few words on each of them, talking about their advantages or disadvantages and why they should be considered for you for a particular use. So one very popular example or class of classifiers is decision trees or decision tree, which basically corresponds to a branching if-else decisions. So for example, based on the features. So for example, here the feature would be whether the last letter is some vowel, and if the feature is yes, then we go here and check other features, and now we branch to the other direction. So if-else on the feature values, and we end up here and the leaves with the label. So this example, I guess, is classifying names into male and female names. So M and F, male and female class, as binary decision here, simplified version. And so the leaf nodes assign labels to that. Why is this a interesting classifier? Is that we can use the path on the features to explain the actual decision. So here's the example of gender identification again, male and female names, and how we train the model is that we want to split the features or prefer splitting features on those that are very informative. And the advantages is the interpretation capabilities. So we really see the features, you can print it out and you see the features and their decisions. And if the features make sense, like in this example, then you would understand how the algorithm decided as such. So it really helps sort of transparency of the models. If the amount of features is small, they make sense, you as a human can understand the model. And of course, there are some issues of decision trees. So, you have to make sure that you have more data than your features because of the splitting, and the order of the features and their independency plays an important role. But overall, decision trees could be very, very nice, baseline for if you have features that could be interpretable and you want to interpret them as such. Another very popular baseline model, still very powerful, still powerful in some cases, and could be a meaningful baseline, is so-called naive Bayes classifier. It has some probabilistic model behind, but at the same time it's very easy to implement from scratch if you really want, because its training and prediction is based on counting features basically. So what we have is a label. So label is a class. We have a label, and for each label in the data set we have the so-called prior probability. So if we have two classes, or two labels, we compute a prior probability for each class in the training data. So if we have equally distributed data set, 50% label A, 50% label B, then probability of A would be 0.5 and probability of B would be also 0.5. So we learn the class distribution. Then we have the features, and we compute the contribution of each feature given the label. So conditional probability distribution of each feature given each label. So this is again something we can count from the data. So we are counting features in the instances, and given the particular feature and given the, let's say, document with a particular class, we are counting the occurrences and compute a conditional probability of this feature given the label. So in this case, we learn, this is called maximum likelihood estimation. So we're taking a fraction of the occurrences of features given the documents. And then if we have a new document to classify, we take the prior distribution of the label and compute and times all features that we find in the document given such label, and we do it for all labels and return the maximum probability prediction. What it really means here, the product of all these conditional probabilities, well, it means that the features are independent of each other. So it means that probability of feature A given label, okay, let's do it differently. So labels will be A, B, C, and features will be 1, 2, 3. So probability of feature 1 given label A is independent of probability feature 2 given label A. And from theory of probability, we know that if we have independent probabilities, we multiply them to get a joint probability. So in this respect, we can, we consider features independent, which is not the case. So maybe words are not really independent in if we classify a document, but this independent assumption works quite well in practice. So it's a nice sort of modeling assumption that might be giving good results in some classification tasks. We can try to go through one example very naively, so without actually computing the numbers, but giving an intuition how it might be actually working. So given a document corpus with 3 classes or labels or categories, being automotive, sports, and murder mystery. So we have 3 labels, and we want to classify a document into one of these classes. And we know by learning from training data that the most frequent class is automotive. So now we have the trained model. And if we want to predict the label or the class on a new document, we, without ever looking into the document, our assumption would be, well, it's automotive because this is the most frequent class. So automotive has the highest prior probability. But then we look into the features to collect the likelihood. So what is there in the data? And first feature is the word dark. So here the words are the features. Occurrences of a word is a feature. So the word dark is an indicator for murder mystery. So the conditional probability of dark given murder mystery is somehow higher than for the other class. Is somehow higher. And then the second feature is football, which is a strong indicator for sport. So the conditional probability here is higher. And this likelihood will sort of push the full joint probability to the class sports. So we would finally classify the document as sports. I guess this visualization will help us as well. So prior probabilities over the classes is just basically the distribution of the different of one of these 3 labels in the data set. So as we saw, automotive is the most common label, or maybe it's different now, but well, let's say automotive is the most common label, and then sports is less likely, and murder mystery. So now if we get a new document to classify without looking into that, we would say it's automotive, because the probability is the highest one. But then we look into this document, and we have several 1 to n features, and for each of the feature we will compute a likelihood for the feature given the the label. So we will repeat it for each label because we want to get a label distribution after seeing all these features for each of them. So we see several features, we compute a likelihood, and this likelihood will sort of reweight our prior probabilities to posterior probabilities, and from them we will find that, even though some class was more common, given the features we saw in the documents, we end up with posterior, that is putting more weight on the label which we want to choose. And as I said already, the assumption of naive bias, why is it called naive bias, is this naive assumption that features are independent of each other. And this is not the case. So, words aren't, if we take words as features, for example, in document classification, features are not, words are not independent of each other. They are in sentences, in paragraphs, in coherent discourse. So there is some dependencies of the words, of course. Why should it work? Well, it turns out that, features independent of each other are actually empirically quite good in some cases for document classification. So, it's just a modeling assumption, and this model is simple but works quite well in practice. So this is why it's often used as a naive baseline, very simple to implement and also interpret. One trick in estimating probabilities in naive bias, it's called smoothing. And why it occurs, why is it important? So imagine you're estimating your parameters using maximum likelihood criteria. So basically counting occurrences divided by occurrences, or there's a division, and it could be that some of the counts are not there. So maybe a feature, let's say word, never appears together with this label. So we would assume that this conditional probability is 0. Well, this will cause some troubles later on when computing the posterior distribution. So maybe you want to avoid it somehow. And what we typically implement is for each of the features or each of these counts, we just add 1 or 0.5 to each occurrence. So even if the feature was never seen in the training data in combination with the label, we would add 1 to make sure that we will never, multiply by 0. We will never get 0 probability. If you think about it, most of things or the feature combinations might be with very unlikely, with very low probability, but they might happen. So the probability is never 0. There's a chance that the word monster, the probability that the word monster occurs in mystery is quite high. And the probability of word monster in automotive, well, it's very unlikely, but it's not 0. So perhaps we don't see this combination of feature and label in the training set, but we wouldn't really assign 0 probability. Something which is super, super low. So we would say by counting plus 0.5 or plus 1, we would say we think we saw it once at least, or 0.5 times. And then when we compute a full probability distribution, it will be a very small number, but not 0, and we wouldn't come into troubles of 0 division or 0 multiplication. We will finish the machine learning zoo by having a look at a library called scikit-learn, which is very helpful library for doing any machine learning, applying any machine learning models out of box in Python. It's not really bound to NLP. It's unlike NLTK. NLTK is especially for natural language processing. Scikit-learn is its general machine learning framework, having many classifiers out of box. And I would recommend you to check it out for any sort of data science-y work that you might be doing. So, not only NLP, but some other. And we will have here some examples on image processing, basically, very simple one. The most famous data set for basic machine learning is the iris data set. So we have these beautiful plants, yeah. And we want to classify them into 3 classes. I guess this data set is coming from early 20th century. And this is not like image classification as you would expect images, but they are described, the plants are described, the flowers are described as a set of features. And this is a very small data set, but a good one to demonstrate a couple of things. So in scikit-learn, we have also data sets. So something we have in NLTK with Corpora, we have data sets in scikit-learn. And this is how you load the iris data set. And it has some description and shows some statistics. So you want to maybe have a look at the features that are already there in the data set. And as I said, these are not the actual images, but some features, which is a sepal length, width, and so on. So if you love biology, then these terms might be familiar to you. They are not really familiar to me. It's been a long time. But we can take it as a data set that is there out of box and don't really care about the features. It's also possible, but not recommended if you do any serious data sciencey thing. We can split the data set into train, def, and test. So we do it basically by indexing the full data set by percentage. So first 20 as train, then def test 2200 and so on. So this is how we create our data sets. There are different ways how you can do that. Some frameworks also provides automatic splitting into train, def, and test, or cross-validation. So scikit-learn also has methods where you say, I want to run cross-validation on that. The K FoLT is such and such, and you can do that. There's many machine learning algorithms out of box working. So the naive Bayes, the model we were talking about earlier, it doesn't matter, what your problem is. If you can turn it into supervised classification with features and labels, you can. If you have a hammer, everything is a nail. So if you have naive Bayes and data sets with features and labels, you can just try it out, no matter whether it's NLP or image classification or I don't know what. So here we get a model, and to train a model, we call the fit function, which returns it fits the instance of the model, and by calling predict on some data, we get a predictions, and we can print the results to see on which instances the model failed. And of course, we want to evaluate our models. So scikit-learn has a package for metrics, and it contains all the metrics we're talking about. So accuracy, precision, recall, and F-measure, F-score, or F1 score. So it has different names, but it's still the same metric we were introducing a couple of slides ago. Scikit-learn also can print out a nice report table of precision, recall, F-score for all classes. What might be interesting here is the support. So it's also showing a number of instances in each of the classes. So as you see, Iris is a very tiny data set. So there's like only 80 instances here. I mean, this is 80 instances we're working with. It could be more, but it's not thousands of instances. It's super small. And of course, we cannot miss the confusion matrix. So scikit-learn can print out the confusion matrix. Remember, it doesn't print out which is what. So is this the gold and this is the predicted, or this is the predicted and this is the gold? So before doing any strong conclusion, I would suggest to double check the documentation of confusion matrix, that it really is, as I'm saying, gold and predicted. It could be transposed. Sometimes some frameworks have it differently. So make sure that you understand what this matrix means, what are true positives, false negatives, and so on. And Scikit-learn has more classifiers from the machine learning model Zoo, so and you can try them out, basically having the same data set and trying different classifiers because they share the same interface for fitting the model, so fitting model using fit and predict. So here we have we define a function try classifier, we put a classifier, and then run training and evaluation, maybe showing accuracy here. And what we're going to try with is the Gaussian naive Bayes, so the naive Bayes model we are showing already before. We will try support vector machines, another very popular classifier from the 1996, were very popular in the 2000. And or this random classifier with this random forest classifier. So random forest is an extension of decision trees, and random forest classifier are still being used in some cases nowadays for some tasks. What we also see here that most of the classifiers have some hyperparameters which are default set to some values, but you might want to change these values. So for example, support vector machines has something called a kernel, and by default it could be a linear kernel, but you want to try Gaussian kernel and so on. So just make sure that you understand what you're using. It has some, it's the models have some peculiarities and some specialties, and you want to make sure you understand the model you're using. But it's very easy to try out things and see what works best. And of course, we see here for this iris data set, the best scores are obtained from support vector machines with default parameters. So although scikit-learn is not NLP oriented per se, it's a very handy tool, very general, sort of small hammer to try things out in supervised machine learning and other data analysis stuff or data sciencey stuff. So I would recommend to give it a shot and try it out and try to play around with different models and different data sets. Try to understand the evaluation as well, or maybe run a cross-validation using scikit-learn. And it's something which comes handy in different occasions, not only NLP. So let me finish this lecture by some more advanced topic, or something which you actually need for the exercises as well. And this is more towards deep learning and natural language processing. So this could be also like a sneak preview to course Deep Learning for NLP, which I'll be teaching in the summer term. So make sure, if you're interested in that, sign up. Happy to see you there. I would actually be happy to see anyone from you anywhere live. So it feels like a YouTuber talking into camera. But anyway, this is how it is. We have to live with that for now. So let's move on to something with deep learning and NLP for text classification. And the task, I guess, is to build a multi-layer perceptron, which is some sort of neural network, using word embeddings, which is also some representation, and classify documents using the Keras API, which is Keras is now part of TensorFlow since a couple of years. We'll be focusing here on the main concepts, not the actual code, because if you need to understand how it works and why it works a little bit. How to actually implement it is a matter of finding the tools and finding documentation. So for example, text classification in Keras is very well described in this TensorFlow tutorial, like the official one, with a long Jupyter notebook. So I would just recommend go there and learn from this beautiful tutorial. But here we will focus on the machinery, how deep learning, or in particular multi-layer perceptron works, because we want to understand a little bit. I don't want to bring all to Athens, so there's a very beautiful 15 minutes video on multi-layer perceptron. So I would suggest you to go there and check this tutorial and check this video. It's beautifully designed and very explanatory. It's not on text, so it's on image. So you would need to adapt it to text later and understand that If there's images on the input and a matrix of pixels, we will have something different, and we'll come to that later. But for principles of multilayer perceptron, MLP, this is really worth checking, and I highly recommend to go there and check this video. But now we're going back to the other part, which is word embeddings. And we'll start with motivation coming from words to some semantics or meaning of words. So why working with words is not really straightforward as features. We have seen words used as features or binary features in different setups for the naive Bayes classifier and others. But why is it maybe complicated? Well, words are distinct items in a vocabulary. And distinct items means that similar words are different items in the vocabulary. And the vocabulary is big, so current English could contain up to 170,000 words. So it's a huge feature space, so to say, if you only consider a single word as a feature. How we encode it typically is so-called one-hot encoding. So we have a large vector of the size of the vocabulary, and if the word is the and the is index 1 in the vocabulary, we put here 1 as the presence of the feature. So each word is basically a one-hot encoding. It's one option. The problem here, as I said, is that if two words have similar meaning, like cat and kitty, these are not the same, but the meaning is sort of similar in most contexts. They are different items in the vocabulary, and we don't capture anything about their relevance to each other. So these are very different topics, and these are the same, not topics, different words and different vectors, and maybe they're as different as kitty and the. There's no meaning of neighborhood. So if we do a document classification, we take typically all the words and throw it in so-called a bag, and we basically create. So if we want to classify a sentence, the cat sat on the mat, we take all the vectors and add them, sum them up, and we end up with some, when the word is present in the document, we put 1, and when there's not word present, then we get 0. So this we throw away the position of the words, but still back of words could be a good representation of features, as we saw, for example, in the naive Bayes classifier. But we can do better, and we can try to project vocabulary to some other space. So vocabulary is sort of a space of vectors, a vector space, and we can try to find a projection to some other space where the meaning plays a role. So here we have, for example, only 50,000 most frequent words. This is our vocabulary size, and we, in theory, can project the words into another space that has a smaller dimension. So for example, it could be 300 dimension vector space. And this space, this vector space, has some nice properties, or could be nice, desired properties, that similar words, words with a similar meaning are similar. So they live next to each other in this highly dimensional space. So here, kitty and cat are very distinct ones, but here in the semantic space, kitty and cat are sort of similar vectors. Not the very same one, but very similar. How can we learn this mapping, from words to this embeddings? It's typically by some modeling. We call it like self-supervision, where we try to predict a word based on the contextual word from some large corpus. So typically we have methods called word2vec or glove. I don't go into details, but there's methods how to train it, and you don't need any label data. So it comes from the self-supervision from the data when you just remove one word and try to predict from the context. So basically it says you can estimate the meaning of the word based on its context in language. So now you know what word embeddings is. It's a vector representation of their meaning, and we can take them, we can train them somewhere, or we can take the pre-trained models, the word embedding models already, which is something I highly recommend you if you start with word embeddings, not to train yourself from scratch, but to take some existing ones like word2vec. And you know what the multi-layer perceptron is, and you want to classify documents. So one issue you might be dealing with, that if you have images and they have all the same dimensions, this is fine, because then you fix your input layer in the network, and all images will have the same size. In case of sentences of documents, they have different length. So for example, if we want to classify the cat set on the mat, so each of the words has 300 dimensions, and we just stack one after each other, concatenate these vectors, we would need 1800 input neurons. Why not? This is fine. But then, how about the cat set in the same network architecture? So if we have 1800 input neurons and we want to classify 3 words, we would have only 900 input neurons. So how can we fit it in? They have different dimensions and it won't work. So different solutions. We can just take the average of the word embeddings. So basically we take the cat set on the mat, all these words, and just sum them up and compute the average. Works quite well in most cases, in many cases, and I guess something which you need for your exercise. So taking the average. We can also pretend we have some limited maximum size of the sentence or of the document, and we start from left and fill the remaining slots up until the maximum size with something called padding, or so we put zeros or some special word there. So it would be, in this case, the cat set would be the cat set, pet, 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 and then we would have the same 1800 input neurons. So this is fine. And there are other architectures that are sort of more advanced, either recurrent neural networks like LSTMs, long short term memory, gated recurrent unit, or convolutional networks. But what you maybe want to do is just take the average of the word embeddings. Having said that, I believe this is just the very basics what you need to start working on your exercises. So what are word embeddings? Is a representation of words in the semantic space. What is multi-layer perceptron? Go and check out a video. And how to use Keras? Just go to the official tutorial and start playing around with the code. Just beware that TensorFlow has changed since version 1 to version 2. So version 2 has Keras already in place, and the latest versions of TensorFlow is 2.4, and the API is evolved and it's sort of stable. You might be, so if you run into troubles and you'll be looking for solutions on the internet, you might end up with finding solutions for the version 1 of version 1 of TensorFlow or some older versions of Keras, which might have different APIs. So make sure that you really work on the version 2 of TensorFlow or Keras. So let's bring it home now. Take-home message. So we learned something about evaluation. Cross-validation is very nice if you have limited data and still you want to employ different training and test on the full data set. We have different metrics. Accuracy is good for balanced data. If you have imbalanced data, you might consider some other metrics such as precision recall or F1 score F measure. We had a machine learning algorithm zoo with different animals, decision trees, naive bias, independent features and probabilistic meaning, easy to implement by counting. We are looking into the scikit-learn library, so something which really is worth considering trying out because it's general machine learning, not only for text. And then we are discussing a little bit Keras and TensorFlow, and we are mostly discussing word embeddings, what it means and how helpful it is to solve some sparsity problems in the data. And why is it useful? for solving machine learning problems in NLP. So supervised learning, their evaluation, and most of the task nowadays is or can be cast as supervised or semi-supervised machine learning in NLP. So it's important to understand the different classifiers, evaluations, and so on. If you're curious about more theory on machine learning, this book of Hasty et al. Is free to be downloaded, so it's free on the internet. And I would recommend to check it out or keep it as reference if you're not sure about evaluations or model selection and so on. So it's very well described as a good reference book. And this is it for today. Thanks for watching. If you have any questions, just drop them into comments. Or into Moodle. I'll be happy to answer them. And thanks a lot.